Hello, my name's Michelle Tyndall. Welcome to this Robot Day webinar. So this evening, the webinar is Mathematics in the Control of Robots, and we're going to be joined by Dr. James Pickering, who is a lecturer at Aston University. His research involves looking at the mathematics of models for the analysis and design of control systems. So he's going to take us through his topic on the mathematics in the control of robots. That will be around 45 minutes, and then we'll have a Q&A. So I will disappear now and hand over to James. Thank you.
So good evening, everyone. Thank you for the introduction. The topic of today is introduced as the mathematics in control of robots. So initial kind of background into myself. So I'm a lecturer at Aston University, which is located in Birmingham city centre. My teaching and research areas are primarily in control engineering and autonomous systems, although I do have secondary interests in mechatronics and robotics and various other applications. I'm a member of the following: so the IEEE Technical Committee on Control Education, the Institute of Measurement and Control, known as the INSTENC, and also the Institution of Engineering and Technology, known as the IET. So I'm going to focus primarily on one robot. So the robot's going to be for collision avoidance or cruise control. I'll then go over the key points that I want you to take away from this talk. And then further on, section 2 and 3, I'll cover ultrasonic sensors, distance measurement, DC motor actuator for longitudinal motion. So the actuators and sensors, and then we'll move on to the control algorithm for collision avoidance. Then I'll touch briefly on model-based design, and I'll show you the robot working before I move on to the conclusions. So my own website here is given here, so www.jamesepickering.com, and you can also find some of the QR code where you'll find some of my kind of teaching material, etc. Right, so first of all, I'm going to talk about the robot for collision avoidance. So this is the robot we're going to use throughout this lecture. I'm not going to cover the bits and bobs behind this right now. We'll get on to that as we move through the lecture. So the aim in this lecture is to design a control algorithm for collision avoidance using a lab-scaled vehicle. What the vehicle must maintain is a 0.1 meter separation distance from an object ahead. So here we've got an object, and the lab-scaled robot is now approaching, and you can see that it now stops within 0.1 meters of the object. You'll notice the negative sign because in reference to the object, it's effectively 0.1 meters behind. And as we move on to the control algorithm design, you'll see exactly why I use the negative number there. Right, so that's what we want the robot to do. That's the aim. In terms of the key components of the robot, we've got sensor, actuators. In this case, there's 4 actuators here, located here, here, and here. That's the underneath of the car. So we've got 4 DC motors and the control. The sensor effectively enables us to see. The control algorithm think, and the actuator take action. Okay, so if we're using, for example, this sensor here, what we want to be able to do, and for some reason my screen's not working, what we want to be able to do is effectively measure distance. So using this sensor here, it's a distance measuring sensor known as an ultrasonic sensor. We want to be able to effectively measure distance to the object, i.e. to the wall that you saw previously. Effectively think, okay, so if we can think, so if we're approaching the wall, we're getting closer. We know our aim is to be 0.1 meters away. And based on the use of kind of the seeing and the thinking with the actuator, we can take action. So if we're a long way away from the wall, we know we can apply effectively actuation, i.e. the spinning of the DC motors to get the car to move forward. And as we get closer, we want the car to slow down, and we want it to precisely stop, or as close as we can, to 0.1 meters to the object. So just like human beings are exactly the way we work exactly the same way. So we observe, we deduce, and we apply. And we do this effectively to achieve what it is we want to achieve. So if we were exactly like the robot walking towards a wall, we'd be using our eyes to effectively estimate the distance to the wall. The brain we'd be using effectively, we'd be thinking, oh, we're getting closer and closer. And the action would be that we would stop as we approach the wall such that we wouldn't collide into the wall. Okay, so sense, effectively use your eyes, your brain, and your neuromuscular system. Right, so the robot's going to operate in such a way. So in terms of the key points, what I want you to take away from this lecture, it's to understand the key components of a control system. So it's the effectively the sensor, the actuator, the control algorithm, and the system. So the system's pretty much what embeds those three things, i.e. the sensor, actuator, and the control algorithm. The next point is signals and data. So because we're using, you can see here, this is a microcontroller, so it's digital. So what I want you to be able to understand is signals and data related to digital control systems. So here you can see various signals and data for kind of measured distance, voltage, error, and then you've got a time graph here. Key point 3 is to understand the 3-term PID control for discrete time. And probably at this point, you're all wondering, what am I doing here? Because when you look at that equation, it looks nasty. But I promise you, by the end of this lecture, you will be able to understand exactly what that means. And it's much more straightforward in operation. That's pretty much what will eventually embed onto the control, well, onto the microcontroller for the control algorithm. Right, so if we start off by looking at the ultrasonic sensor for distance measurement. So I've introduced you to the basics of the robot. And the first thing I spoke about was the sensor with the ability to see, or in our case, kind of observe. So this is an ultrasonic distance sensor, HCSR04. It's used for measuring distances between 0.02 to 4.00 meters, well, 4 meters. So it's got a little bit of a blind spot initially. It's got accuracy of plus or minus 3 millimeters. So in terms of how this operates, because what you'll notice here is it's got 4 pins. It's got voltage, ground, and then it's got effectively a pin for the transmitter and a pin for the receiver. So what one of the pins does, it sends a signal effectively to send out a wave, the original wave, and that's from the trig pin. If you look on the trig pin, you'll see this. Bounces off an object, reflects, and here you've got your reflected wave, which is the echo on the ultrasonic sensor. So transmitter and receiver. For this, what we want to do is we want to use this ultrasonic sensor to effectively measure distance. So calculation for distance measurements given here, where d is distance, is equal to t, which t is the distance between the trig and the echo, so effectively the time that it takes for it to bounce off and return. C is the speed of sound, so approximately 343 meters a second. It's an ultrasonic sensor, it's using speed of sound. And then the reason why we want half is because we only want the distance, obviously, for the signal to actually the object. We don't need the distance there and back. So this here, we can determine the distance or estimate the distance using this sensor. If we're looking at this in terms of the operation, you can see there the car's just approached the object. It's minus X meters away from the object. What we're going to configure this is, we're going to configure it with a sample time of 0.01 seconds. So sample time is going to a little bit confuse you. Well, that means it's going to effectively, the microcontroller on board here, hooked up to the sensor, is going to collect data, distance measurement data, every 0.01 seconds. Okay, so every 0.01 seconds, think about that, it's sampling and it's collecting a distance measurement. So if I go back here and I go to the video, here, what I've got is the ultrasonic sensor here attached to the front of the car. And you can see on the y-axis here, it's effectively distance. So originally it's minus 0.14 meters. And you can see as I'm moving the ultrasonic sensor closer to the Rubik's Cube here, you can see the distance is getting obviously smaller. Okay, so we're capturing here on this video in real time distance measurement data. And it's capturing it every 0.01 seconds. So it's capturing a distance measurement for me. Right, so that's useful. So on this robot now, I can effectively measure the distance to an object by using a simple sensor. So in control, so that video here that I've got is pretty much, it's the same video as before, it's just there so you can have a watch of it again while I'm talking over this next slide. What we do in control is we tend to represent things with blocks and effectively lines. So blocks normally we use to represent components, so in this case the ultrasonic sensor, and then lines are to represent signals. In this case a line, and it's got an arrow here which represents direction. The signal or the data coming out of this ultrasonic sensor is the sampled output. So output is Y, and K as the sample. So it's the output, which is denoted Y, and then sample, which is denoted K, and the notation we use is Y subscript K. Okay, initially, some of these early slides I'm going to go over, these are the ones that you need to pay attention to and make sure you understand, because then it will all tie together at the end. And that pretty much is giving me measured distance in meters. So you can see measured distance in meters on the y-axis here, although it's not on here because it doesn't display it in real time when I'm doing this, but you would see measured distance, the axis is along there. So this now is how I represent it in terms of graphical form. So I've effectively zoomed very, very closely into 3 samples. So I've collected 3 samples from that distance measurement, not actually from this one, because you'll notice obviously the values here are much larger, but you get the idea. So on the x-axis, I've got discrete time, and the notation I use is k minus n. And you'll see here I've got k minus 1, k minus 2. K is my current sample, k minus 1 is my past sample, and k minus 2 is my sample before the past sample. So effectively, I've got 3 samples there of the measured distance, where k is my current sample, so current sample in time. Right, as I said to you, the sample output, y of k, is the notation we use. So for the current sample, that sample, the notation I use is y subscript k, so that's my current sample. K minus 1, that sample there is yk minus 1, so it's my past measured output or sampled output. And then y subscript k minus 2 is obviously my previous one. And you'll notice that these relate to obviously distance measurements here. So I hope by this point that's making sense. So your sampled, effectively a sampled data control system, you can see that I've got 3, well initially I'm just measuring the distance, but I've got 3 samples. So current, past, well current, and then well, if I go 1, 2, 3, one's current, one's past, and the one's even obviously further behind. So discrete time, measured distance, that's there, that's important. That's one of the first important things that you need to make sure you understand. Then if we move on to DC motor actuator for longitudinal motion. So what I'm using here is effectively, I've got 4 DC motors, I told you at the start. These are mounted to the wheels, these are in brackets, and if we supply these with a voltage, a potential difference, you'll get the shaft on the motor spinning. What I'm initially going to use for this is a sample time of 0.2 seconds. I'm using this initially for visual reasons. And what I'm going to show you now is a video of effectively me supplying between 0 and 5, if you look there, 0 and 5 volts to the actuators. So what you'll notice on this graph is 0 there, 0 volts. Okay, it's very hard to see, and it goes all the way up to 5 there. So this is, again, a graph that we're seeing in real time. And you can see there when I'm all the way up, you can see here I'm on 5 volts, right? What you're seeing is a staircase signal. So what's happening is effectively the signal's being held for TS seconds. The signal's being held for 0.2 seconds because that's what I've told the controller to do. I've told it to basically output the voltage or changes the voltage every 0.2 seconds. Okay, the reason why I've done that is because I want you to see the staircase rather than pick the original sample time I did for the sensor, which was 0.01. Right, so you're seeing that. You're seeing the brightness of these LEDs change as I increase the voltage. So if I go all the way up to 5, the LEDs are very bright. Take it down to obviously 0 volts, the LEDs are going to be off because there's no power being supplied. Right, so that's my 4 DC motors. What you're seeing there is effectively by using that tab here, I can in some senses control the rotation of the DC motors, the 4 DC motors. So I can at some point just turn them off, or I can turn them on full power. Again, this is obviously on a platform. I've done that just so that obviously I don't want the car going anywhere. So again, this is an illustration. As I said, the width of these is effectively 0.2 seconds. However, the illustration I've got here uses a time of 0.01. Because one thing you need to be consistent is when you're developing a digital control system for a robotic application, you need to make sure you're consistent in your sample interval for the sensors and the actuators. So for this one, it's the same idea. So we've got discrete time. Okay, my pen's a bit bit sluggish. We've got discrete time on the x-axis. On the y-axis, I've got voltage. You'll see again sample. So we've got K, K minus 1, K minus 2. So current sample, and then the current sample, K minus 1 is my past sample, K minus 2 is my sample from before. So these are effectively the action here, because it's always the bottom left corner, the action that's being supplied by the algorithm. So I was the algorithm, well, I wasn't really the algorithm, but I was the operator, and then the algorithm was basically saying, well, the algorithm on board, the microcontroller was basically saying supply an algorithm output of this, which relates to this voltage, and obviously the voltage was changing, that was supplied to the DC motor. So that one you can see UK U star K, and U is the notation that you normally use for kind of algorithm output. The reason why I use a star is because it's a staircase here. So when you get a staircase like this that we're seeing, we normally use star. So UK star. So you can see here. So current sample UK star, it holds that voltage constant for TS seconds, which we use the notation for the sample interval. UK minus 1 star and UK minus 2, and you can see the voltage is changing as obviously some changes happening in terms of the algorithm. So again, what we do is we represent this, the algorithm, in block diagram form, and we also represent the DC motor, actuator and system in block diagram form, as you can see here. And then in between here, the line with the arrow is effectively a signal. So here we've got our algorithm output, UK of star, and that relates to a given voltage being supplied to the DC motor. Right, so that's your second takeaway point. So you need to make sure by this point you're aware of voltage in terms of how we represent it graphically and in terms of a sampled system. Because this is the point we're at now. So we've effectively used the ultrasonic sensor to measure distance to enable us to see. So I don't know why my pen's not working. Maybe I'll move to my mouse. So we've used the ultrasonic sensor to measure distance to get the sampled output, Y of K. We've used like an algorithm, although I haven't gone into detail of that, to effectively change the voltage supplied to the DC motor. And you can see the corresponding signals here for the voltage and the measured distance. And you can see digital microcontroller and the system. Right, so that's where we're at so far. So we've got sensor, we can see. We've got actuator, so we can do. So if we move on to the next part, what I've done here is I've introduced something known as a summing junction. So you'll notice here that I've extended this sampled output here, which is your measured distance, and I've effectively joined it up with this summing junction. Summing junctions here allow us to add and subtract signals. So what I've got here again is another line to represent a signal. This is for the sampled reference, and I'll use the notation R subscript K. Our desired distance is minus 0.1 meters. So what we effectively do is, well, I'll get on to in a minute, is this calculation here. So what we need to determine in a control system, and this is very, very important, is the sampled error. In here, in this case, it's denoted E subscript K. Because our sampled error is effectively the difference between what we desire, i.e. our sample reference, and what we're actually measuring. So if there's a difference between those two, you've got an error, and that's pretty much what drives the control system. And it works exactly the same way, you know, like you're the human being walking towards the wall, you know you want to stop at a given location. Before you get to that location, you've got an error. So this formula, it's nice and simple. It's just E subscript K is equal to, so the sampled error is equal to the reference, the sampled reference, take away effectively the sampled output. So this equation here determines the error. And what you'll also notice is here, I've introduced something new. So rather than having algorithm, I've introduced control algorithm, because now what we've introduced is something known as feedback. So feedback effectively enables us to, and this is the feedback loop here, and I'll just reiterate, it allows us to compare what we want to what we're measuring, and then we form an error, and then effectively we want to configure the control algorithm such that's going to compensate and minimize the error as much as possible, such that we achieve the overall goal, which the overall goal is the desired distance in this case of minus 0.1 meters. So just to kind of show you some examples, so what I've done is I've just taken this area here and I've just got this here. So I've got some calculations for example. So I've got E of k is equal to R of k minus Y of k. So that's the formula that you saw previously. We know that R of k is our reference, which is minus 0.1. And these numbers here are used from the earlier, they're used from the earlier example. Take away minus 0.230. The reason why it's minus, because if you think the obstacle, the reference is minus 1, the distance or the car is further behind, so it's minus 0.23. So what we then form is an error here, 0.130. Then that's the current error. The past error, so one sample back, so like historic data, is RK minus 1, take away RK minus 1, which is, again, the reference is exactly the same. And again, we're going to use one of the values that we used previously, and you can see there the error now has changed. Then the final calculation, I won't spend too much time, but you can see E of k minus 2 is equal to RK minus 2, Y of k minus 2, which again, the reference is exactly the same because the reference doesn't change. That's what we want. And you can see the measured value now is minus 0.236. Again, the value we used earlier, and you can see how the error value has increased there. So what you'll notice if you're looking on this diagram, so this is another thing you need to become familiar with, is the current sample, past sample, and then the historic sample before that for the discrete time here relates to E of k here, which is 0.130, E of k minus 1, which is 0.134, and then E of k minus 2, that one, which is 0.116. So you see, as in discrete time, we're sampling, we're sampling the reference, we're sampling the measured distance, and we're sampling these with the same sample time, so 0.01, so sample. On board the microcontroller, we are determining, basically it's just this little simple equation that you'll see at the end, we're determining the sampled error. Okay, and it kind of makes sense. Well, the difference between what you want and what you actually are getting is your error, and that's what's going to drive the control. Right, so just to take this one step further, so what I've introduced here is effectively a control algorithm, but I've just introduced here PID. So PID is the method we're going to focus on of control. So this is proportional, integral, and derivative control. So this is the method primarily used in industry. I'd say 95% of control systems are some form of PID. So what the PID effectively control enables you to do, so if I go one step back, the PID control algorithm, so think of this as like it's going to be an algorithm eventually, but it receives this sampled error and it's effectively allows you to use that sampled error for 3 different things. So what you can do with the sampled error is you can multiply it, you can integrate it, or you can differentiate it. So if we just, for example, look at the current error here, sampled error, we can just multiply that, and we would multiply it with a proportional control gain here, KP, and this will make more sense as I go through. We can integrate it. So what we can do is, for integration, we need the current and we need the past, and then we can effectively work out the area below here. So the integral below these 2 sample points. And then what we can do once we've determined the area of that, we can multiply it on an integral control gain. Then the final thing, as I said, is the differentiate, which is effectively taking the rate of change of the error. So it's effectively the rate of change of E of k minus 1. So we can effectively estimate effectively the rate of change of that. And then once we've determined that number, because it's obviously going to correspond to a value here, just like the area is going to correspond to a value, the error is going to, and we can multiply that by a derivative control gain. Right, so that's your 3-term PID. Again, very, very important. Proportional control gain is where we'll start because it's the simplest, and a lot of application industry you just use a proportional. So the proportional control gain in terms of the control algorithm is just this KP value here. This multiplies effectively by the sampled error. So E of K has a number, K subscript P would also have a number, and there's various ways in terms of tuning methods that I'm not going to detail right now, how you would select that number. And that then effectively, those multiplied gives you your control algorithm output. So UK of star is equal to KP multiplied by E of K. So you're probably thinking, well, yeah, this looks great, but what is this actually going to do to my system? So if we look here in terms of graph, we've got a graph here, and I've got an illustration here to show you two different ways. So if, for example, well, here I've got my reference, actually, I should just say that. My reference is minus 1.0. So if I put a proportional control gain, KP, again, I'm not going to put any numbers in because this is just for kind of, just to give you a rough initial idea of what's going on with the proportional control gain. What you'll notice here is the proportional control gain given by the orange, you'll see that the distance increases and then it settles at a value of minus 0.18. And again, you can see this represented on this diagram here, where we've got the object, we've got the reference, and you can see the distance between the car here and the distance and the reference here is minus 0.18. So we've got something known as a steady state error. So a steady state error is the difference between what we desire, i.e. minus 0.1, and what we actually get, in this case, minus 0.18. Right, let's increase the proportional control gain. So we just do 2kp. What you'll notice now is the steady state error has actually, in fact, decreased. Okay, so the steady state error has decreased. And then if we increase that even more, what you'll notice is now the steady state error has, in fact, decreased. But what's happened is now the car's traveled here and it's overshot, and you've ended up with a final value of minus 0.08. Okay, so you've still got a steady state error, and in fact that it's overshot by, well, in this case, minus 0.08, and obviously my reference is minus 0.10. So proportional control gain on its own, it will effectively reduce the steady state error, but it doesn't always eliminate the steady state error. Sometimes proportional control gain is sufficient control on a given application, so such that you don't need to go to further methods that we'll talk about. It will also, proportional control gain, as you increase it, will increase the response time, which is kind of obvious because you're effectively putting more power into the system. The response time is the time taken that it effectively takes to achieve the final value of the system, and the final value of the system is being effectively when the car stops. But you are limited in terms of that based on the actuator and obviously the system that you've got. Right, so if we move on to the integral control, this gets a little bit more difficult, but you'll see that the maths is actually very, very straightforward. So if we look at the current sampled error, and the past sampled error, what we want to do is determine the area under the curve. So this area here in blue. So we're going to use the trapezoidal rule for the integral, and it's effectively given by the area between the two samples, which is effectively the value of E of K, the value of E of K minus 1, divided by 2, multiplied by TS, where TS is obviously just your sample interval. So i.e. it's the mean of the two vertical heights times the width, and that gives you the area. And you can see here effectively I've determined the area underneath there. Right, so if I go one step further, what I can also do is determine the area or the integral of E of K minus 1 and E of K minus 2. So you can see here I'm using the formula, it's the same formula, the only thing is obviously I'm taking different samples. However, we don't really do this, and the reason why we don't do this is because if say for example you had a system that was operating for 10 seconds and your sample interval was 0.01, you would end up with a really, really long calculation, and it just in the end your control system would probably just fall over. So what we actually do is we only actually take into account the first integral, and then the rest of them, what we do effectively is we sum them up. So the previous int, which includes this one and any previous ones in terms of sampled historic data, in terms of the integral, we effectively just sum up. The integral will effectively, it's effective because it will hold the control action in place. So say, for example, if your error becomes 0, the integral will hold the control in place. So it's very important to have this previous int. And as with the well, any of the three control terms, you can see the control algorithm output here. So UK star is equal to K subscript I. So this proportional integral control gain. So integral control gain effectively multiplies by the area of the first integral and then all the previous integrals, right? So that's pretty much how the integral works. In terms of the previous int, so it's effectively previous int is equal to previous int plus the first integral. Right, so integrals, very, very useful. And the reasons why it's useful is, as you can see here, so you can see proportional control gain in the orange here. That's effectively the worst case, what we saw for the proportional control gain. Now I've introduced the proportional and integral control, which is given by the red line. And what you'll notice is now we've got zero steady state error. So we've gone from having steady state error to having zero steady state error. So we've effectively achieved the reference. So if you go down here, this is the car with the PI controller on. So the algorithm's on board the microcontroller. We're getting zero steady state error. Great, we've solved the problem. We've achieved the aim. So the integral is great in terms of what it does. It eliminates the steady state error. But one point I want to make is that there's not all control systems have steady state error. So there's certain types of systems that you don't want to put an integral on, because if you do, you're not going to get very good control. So for a system that has steady state error, putting on an integral will eliminate the steady state error. So then if we finally move on to the derivative control. So the derivative control here is given, well, you can see it's given here. And as I told you before, what we wanted to do is effectively take the current sampled error, the past sampled error, and we want to effectively approximate the derivative. So what we're going to use is the backward Euler approximation for the derivative. And it's effectively given by the average slope between the two samples. So E of k minus 1 divided by TS, which is your sample interval here. And that gives us the blue dot there. And the blue dot is, well, the dot there is effectively our approximation of the derivative. There's a few things you have to be careful of with sensors that tend to have noise on, and that if you end up with effectively selecting a big derivative control gain, you can end up with bad control. So noise on sensors is one thing that you need to be aware of. So then in terms of the control action, so control algorithm output, UK of star is equal to, again, KD. So this is the derivative control gain multiplied by effectively this estimate here of the rate of change of the error. And that there is effectively your PID. But what I'm going to do first of all is just go over to you how the effects of the derivative. Although really we achieved what we wanted to achieve on using the proportional integral, it might be that we want to, for example, make the system response time faster, stiffen up the control, etc. So it might be that we move to the full PID. Because the derivative gain, you can see here, what it's done is it's made the system response effectively faster. It's got to the final value faster. And a lot of applications, it will like stiffen up the system, like I said. So you can see here again, it's achieved zero steady state error. So to summarize here, you can see the block diagram here. So you can see the ultrasonic sensor with the sampled output, which is your measured distance. You can see then that being subtracted away from the sampled reference, which in this case is minus 0.1 meters. We're then forming the sampled error. So just remember the sampled error is based on the reference, take away the sampled output. And then in the case of the proportional control gain, well, the proportional control, it's just the sampled error multiplied by the KP. So that's going to give you control action here. In terms of the integral, it's the area underneath effectively the current sample and the past sample, plus all the previous areas, all the integrals determined. And that's multiplied, all that's multiplied by this integral control gain. And that's there going to give you an output there. And then finally, the derivative here. So if I just put an I there and I'll put a D here, the derivative here is effectively just working out the midpoint between, well, it's estimating the midpoint between the two, between the current sample and the previous sample. And that multiplies by your derivative gain here. So these three gains here will be given a certain number. The number is based on, well, you can trial and error if you've got some understanding of the effect of these three gains. As I just told you, the proportional will increase the will make the system response faster. It will help reduce the steady-state error. The integral will eliminate steady-state error. The derivative will get rid of if you've got any oscillation on your system response. It will make the system response faster, stiffer. So those three terms and what you select for those three numbers is going to make a huge difference. So in terms of these three, they're going to output a value. They all sum up together. So you can see here plus, 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 and then they form your control algorithm output, which is effectively a voltage that is supplied to the DC motor. So in summary, the equation's given here. Well, not in summary, the equation's given here. So UK of star is equal to, you can see, proportional control gain multiplied by error, plus the integral multiplied by effectively the area of the integrals, plus the derivative control gain multiplied by the midpoint of the current and the path sample. The free term PID will give desired system performance. But again, like I say, you don't need to use all three terms. You can get away with using a proportional, use a proportional. If your system has no steady-state error, you don't need to use an integral, etc. So we're looking in terms of how we actually implement this equation. What I've got here is some sample code. So you can see here reference is equal to minus 0.1. Error is equal to reference take away measured distance. Int error, so the integral error, is equal to effectively error take away last error divided by 2 times by elapsed time, which is just my sample interval. And you can see there's a plus there because what that's doing is summing up all the previous values. My diff error, which is my effectively rate of change of the error, my derivative, which is equal to error take away last error divided by elapsed time. So what you'll see is those equations are the ones that we effectively derived here, and we've just literally written a line to describe each one of those. So in terms of the output, so the control output, you can see here, output is then equal to Kp, Ki, Kd, and then it's multiplied by the error, multiplied by the integral error, multiplied by the derivative error. What you'll notice is that I've got here three values for the proportional, integral, and derivative. So 80, 10, 5, whatever. These are very, very dependent on what the system is. So you're probably wondering, well, how are these actually determined? So I'll explain a little bit on the next slide. Once this effectively code is sorted, though, what we can do is embed it onto effectively the microcontroller here. And this microcontroller, as you can see here, measured distance. Effectively, you're going to name some measured distance. So it's going to bring in information from the sensor. Measured distance information is going to come in every 0.01 seconds. And then your output to your motor here, it's effectively going to be a voltage. So your voltage then is going to be sent out. So your microcontroller is going to send a signal to send a certain voltage to the 4 DC motors. And that's pretty much how it works. So your sensor's seeing, it's capturing distance data. It's then forming an error, which is based on comparing it to what we want, what we're measuring. And it's then all that data there. So the current sample, the path sample, are being used as part of this proportional integral derivative control. And based on that, it gives you very, very powerful control. So you can pretty much get your system in this particular application to achieve the desired outcome. Right, so I'm only going to spend a couple of minutes on this because I think I'm running out of time. I think I've already spoken a little bit too much. So in terms of model-based design, this is one method that you can use effectively to tune a control. So it's a model-based design using a package such as MATLAB and Simulink. So what it relies on is effectively a mathematical model of the open loop system, including the actuator. So if I get a mathematical model that effectively represents the motion of this car going forward, and then I can kind of then implement it in the maths. You can see here what I've got is feedback here, feedback, you can see here, and then it goes into a summing junction with a negative. Okay, this is known as negative unity feedback. And the reason why it's unity is because we assume an ideal sensor. We've got here our reference. So the reference here, minus 0.01, is compared to the measurement, which is the output of the system. And then you form an error here that then, in this case, multiplies by this proportional control gain, which is a discrete time PID controller. Discrete time because we're working in digital. So what I could do in this simulation, you're not going to be fully aware of this because obviously I'm being very, very quick on this. But what we can do is we can effectively tune the PID controller within this simulation. So having a mathematical model of the system, I can effectively, first of all, start from proportional, see the effect on the proportional control gain, and what I get is effectively rapidly available results. So you can see here, effectively, if I was undertaking PID tuning, so selecting the values for the proportional integral derivative, you can see results very, very quickly. So you can see here the references, well, it's difficult to see because again, it's from a scope, is minus 0.1. And you can see the car starting from about minus 0.28. And you can see it ending up at the reference using the proportional control gain. So using simulation, I've initially got an idea that, okay, although this isn't actually an exact model of the car, I just approximated a model. I can already see that I can probably get away with just using a proportional control gain for this particular application. So model-based design, although I haven't covered it in much detail, it's one method, but I feel like with time, you do get used to the effect of the proportional, integral, and the derivative control gains. So you get quite good at kind of understand, if you can understand your system, i.e. apply an input to a system, maybe a voltage, measure the output, you can normally get quite a good idea of what control method needs to be applied. But again, this is probably, if you want part 2 of this lecture, it would be part 2. So initial testing, so the robot working. So what I've got here is initial testing for the control algorithm and electronics. I'm aware that I haven't covered much in terms of the electronics and much in terms of the software in this talk. But what you'll see is proportional control initially tested. You can see the reference here, which is on this red line. And what you'll see is on these graphs is I've got measured distance, which is about minus 0.017. And you can see here my error, which is about 0.07. And you can see a voltage here, which is about 1. So as I move this, what you'll notice is that the measured distance is going to, well, when it got to the reference, it should be a value of minus, well, it will be a value of around minus 0.1. The error should go to a value of around 0. And the voltage, when we achieve the reference, the voltage should become 0 because the DC motors will actually, in fact, stop. Okay, so measured distance, we want that to be 0.1. We want the error to become 0. Because obviously the difference between what we're measuring and the reference, we want that to become 0, and then the voltage to become 0 because we want the motors to effectively stop. So then, if I then go on to a further video, so what then I've done is I've done a further investigation of just using the proportional with the aim of obviously achieving the separation distance from the object ahead. So if I just run this video, so again, the reference is this red line. It looks a bit wonky. So Kp equals to 400. You can see I'm getting large steady state error. So a large difference between what I want and what I'm measuring. Kp is equal to 600. Again, smaller error. It's as we'd expect, what I told you earlier. Kp is equal to 800. That pretty much looks spot on for me, good enough. Kp is equal to 1000. You can see now I'm getting overshoot. And then if I go Kp for the proportional control gain up to 1200, I'm getting larger overshoot. And then finally, I'm going to look to Kp is equal to 1400. You see I'm getting quite a large overshoot. What you'll notice, the LED lights turn off because I've kind of configured the LED lights such that if it goes to the reference, they switch off, and you can see they're blinking when they're at the reference because they're effectively not being supplied with too much voltage. So there we've achieved the goal or the aim of 0.1 meter separation distance just by using effectively a distance measuring sensor, forming a reference, well, setting up a reference, forming an error, having a proportional control gain that effectively multiplies by the error, and then the control algorithm output is effectively just my voltage. And you can see here just a graph. So we've got here distance, well, time on the x-axis versus distance. And you can see here the reference, which is minus 1.01. And then you can see the measured distance here in the blue. Okay, initially, I think the robot comes up and then it does jutter a little bit at the line, when it stops, and then it jutters over and then pulls back. But you'll notice overall it's pretty good. It achieves, I would say, pretty much close to no steady state error, i.e. the measured distance is equal to the reference, and i.e. an error of close to being 0. Right, so I've realised I've gone on for probably a little bit longer than, probably about 45 minutes. So just in conclusions, the key components of a control system have been described. So sensor, just want to go over this again, the ability to effectively see. So it's effectively as we do to observe. So it's measuring distance. The actuator is to effectively to take action or to deduce as we do. And the control algorithm is effectively to, well, think of it is effectively to, is to think. And then finally the system. So the sensor measuring distance, actuator changes, the control algorithm enables us effectively we can configure something like a PID controller to achieve the desired performance of the system. Signals and data for a typical digital control system have been introduced. So I've introduced you to the idea, well, distance measuring sensor, sampling data every sample interval or sample time, so in our case 0.01 seconds, and introduce the idea of current sample, past sample, well, and then beyond that, just historic data. In terms of the actuator, again, it's the same idea. You've effectively, what you've got there is a staircase. So the voltage supplied to effectively the actuator is supplied, is changed based on the sample interval or sample time. This needs to be consistent with the sensor. So it's like a staircase signal. It's known as a hold. It's holding the voltage for the sample interval. And then finally, the error signal. So the error formed based on the reference minus the reference minus the measured, well, the sampled reference subtracted from the measured output, and that forming the error. And the error is pretty much what drives a control system. And then finally, introduce you just to a graph at the end, which had distance against time, and there's the time solution. Okay, so the sample and the data, well, the signals and the data, that's the sample data control system, effectively for the microcontroller. And the graph is for the time solution. That's actually what it would look like in real time, or the actual physical car, the displacement of it. And then finally, the free term PID for collision avoidance has been demonstrated with a practical example used to highlight its effectiveness. So I've gone over proportional and pretty much how we use proportional for our application. Integral and derivative. If we were to introduce perhaps a object that had some dynamics, so for example, if the car was following another object that maybe was changing its speed, it'd probably be likely that we would have to introduce an integral and derivative. But the initial case I just showed you today was just the most simple, and it was actually the most simple for me to set up on my desk. So integral and derivative are also very, very useful because we can effectively eliminate steady-state error. With the integral and the derivative, we can do things such as reduce the oscillations on the system response, or make the system response faster, stiffer. And yeah, I kind of would suggest to everyone to have a look and to build a little robot using a free term PID controller or some sort of application, and go through the process of introducing the proportional integral derivative, because you'll see how effective this control method is. It's very, very powerful. Right, so I'll get back up that page and I'm going to say thank you, and that's me pretty much done. Thank you.
Thanks a lot, James. I'll give you, I always do this on virtual lectures, give you the round of applause that I'm sure would be present in a lecture theatre. Yeah, it's been quite nice actually. We've had quite an active chat, which Stephen, another of the IET volunteers.
Oh, 97 messages. Wow.
Yeah, don't try and catch up with that. So we'll start going through the Q&A. There's quite a specific question from someone who's, I think, studying robotics, and they're asking for help with a specific project. So I'm not sure if you're familiar with NLMPC control algorithm.
Yeah, nonlinear model predictive control. That's something actually I could have said that there's not just three things you can do with the error signal on the PID. You can also do model predictive control. So you can effectively predict the error, which is the question that Jack's got.
Yes.
So yeah, nonlinear model.
He has asked for your email address, so maybe you've got your email address on the screen, right?
Yeah. If anyone's got any questions, if I can't answer, I can try and point you in the right direction. So control@Pickering.com. Yeah. Oh, he's got the topic, optimized vision control. Okay, that sounds. Yeah, that sounds good. Yeah, just drop me an email, Jack.
Yeah, The next two questions are related to on your slides. I think there's a minus, which should be a plus on the trapezium rule.
I put a couple of errors in there to make sure that people were following.
Yeah, I know. So well done. That's Rob and John.
Well done, John and Rob. I'm going to sack the person that proofread my presentation. No, I'm joking. It's thank you. Where was the error? It's slides for integral plus a divided by 2. Oh, okay, yeah, I'll have a look at that. Okay,
yeah.
thanks. If there is a mistake, I'm glad that you spotted it. It means that next time I give this presentation,
it's on the when you're talking about the integral section, the integral control, it should be ek plus ek minus 1 over 2.
Oh, okay, yeah.
But yeah, that's that. It does that's just a minus sign.
Yeah, no, it's good that that people are spotting this. Yeah, that's good. Yeah.
Okay, and then someone I don't. This is an acronym I don't understand. How does the error dependency follow the ADC you chose to use?
How does the error dependency follow the analog to digital conversion you choose to use? Analog. Let me just go to the. Let me explain it. So analog to digital conversion. How does the error dependency follow the? Okay, so I didn't really talk about things to do with resolution and data acquisition. I assume that's what you mean. So really, like in terms of using a microcontroller, it does have obviously a resolution. Well, it depends on the number of bits. So it tends to be for the analog to digital conversion, it's 10-bit, which means for the sensor it would have effectively 1024 different levels between 0 and whatever the maximum value was, and that then the distance between those would determine your resolution, which I didn't go into in this lecture. I think that's what you're asking. But however, in this particular application, I have it's using a digital sensor anyway. So the ultrasonic sensor is actually a digital sensor. So there's no analog to digital conversion here anyway. Yeah.
Okay. Yeah. So how would you normally use multiple PID controllers, for example, in adaptive cruise control, where a robot manages speed and distance from the car in front of it?
Okay, how would you normally use? You can, for example, you can. It would just end up being that you would have effectively something that looks a bit more complicated than what I've got here. So here, obviously, we're just doing displacement. If I was doing speed, I'd effectively have a different sensor, and there might be a connection between the two controllers. Yeah. Something, again, if you're interested, I can try and pinpoint you in the right direction.
Yeah. Okay, a question about more career focus. So there's somebody who I think is studying their GCSEs at the moment. I've seen them talking in the chat, and they're looking to go into a career in robotics. They're not sure how to get there, thinking of going to A-levels and then university, but they're not sure about what courses they should take. Do you have any suggestions?
Okay. Maths are certain you're going to need to take A-level maths and physics, I would imagine. I'd just say your A-levels, maths and physics are the two that you need to be moving into kind of a career in engineering, a career in control, robotics, autonomous systems. Yeah, they're all the same sort of thing. Yeah,
I think it generally for I mean, I actually didn't study engineering. I work as an engineer now. I studied physics, but if you do maths and physics, you can generally study any engineering course across. You can civil, chemical, whatever. So they're quite solid choices if you're quite set on going to university and studying.
Yeah, you're also not limited on what degree you do, because if you do a maths-based degrey, you can normally slide over into robotics, engineering, these sort of disciplines. You're also not limited.
Yeah, you can do more. It depends how specialised you want to be, but kind of with postgrad study as well, you can tend to change your direction, specialise as well. So There's a specific question asking for your MScript codes. Do you share any of your?
I've got no problems. Yeah, again, if you drop me an email, I can.
Yeah.
With these scripts, though, if you want to, I assume you want to try the robot stuff. I've got no problem putting it all on my website at some point if people want to go on there. But the only thing is you do need to have a license for the package that I use, which is MathWorks, which is MATLAB, and the Simulink add-on as well. So you do need MATLAB and Simulink, because I all the kind of the demonstration I use in here all uses automatic code generation. So I basically design my control system using package known as Simulink. I click a button, although I didn't actually show you anything today, and it basically converts it from my Simulink diagram into C code for me onto the microcontroller.
Is that is Simulink something people generally can get access to through devices?
No, not unless you're industry or university. So yeah.
I mean through university.
Difficult. Yeah. You've got Python, which is or Arduino, which is open source. So you can do the same things I've done here.
Yeah.
You can use tools such as that. The only thing is you don't have Simulink's great because I can visualize signals in real time, and I can change properties in real time, which you can't do using Python or Arduino. But yeah, like I say, using Simulink, it's great because I can change things in real time, and I can see the effect that they're having in real time. So the little car, I was playing around with it literally just in front of me yesterday, getting it to work. And I was just changing things, quickly implementing it. I was all doing it on my desk.
Yeah, it's very nice demonstration. Yeah. It's really good. Yeah. A more technical question here. If your motors can only be updated every 1 second, do you have to use this as your sensor sample time?
Okay, so if it's updated every 1 second, you don't have to, but you'd have to. I think you'd have to configure it somehow in the software that you're using, because I use the package I use. I have to be consistent in my sample interval.
Yeah.
But I assume that you could collect more data from your sensor, but it would be likely because obviously your forming your error is based on the control output, and the measurement is based on the sample interval. So although you're taking more information, you only really need information every 1 second from that sensor anyway.
Yeah.
The rest of the data would be pretty much redundant anyway. Would not really very useful.
Yeah. So is trial and error the best or only way for determining the control gains, or is there a more calculation-based approach to try without trial and error?
Yeah. So nowadays, I tune my PID trial and error, because there's basically a table. If anyone wants to do control, you'll remember the PI values, and then you'll see the system properties like rise time, steady state error, and you know the effect in your head. What happens as you play with the free terms? Well, once you've got a bit of experience doing it, there are numerical methods. So you have things such as like the Ziegler-Nichols methods that you do, but they're for kind of given applications. So it could be a system with a certain amount of overshoot. So if it oscillates a bit, but overall, again, like I said, I touched on briefly on model-based design. Within there, what it has in there is within this package, it has a PID block. Let me go to there. Let me go. Yeah, it has in there this PID discrete time. It has a tuning algorithm in there. So it has something known as auto tune. So you click auto tune, and it has a couple of tabs that you can effectively move about to make the system response faster, more aggressive, etc. And what it does while you're doing that, it will show you what your estimated system response is going to look like. So it will show you effectively this here.
Yeah.
Okay, so again, that's one method. So you've got simulation tools, you've got hand methods, and you've got trial and error. I tend to use this model-based design approach, and also trial and error. I don't tend to use the numerical methods.
Yeah. Okay.
Yeah.
Okay, someone who is currently studying their A-levels and wanting to do aerospace at university. Mm-hmm. Oh yeah, I think this was somebody who was maybe asking about their personal statement. So is there anything that you think universities kind of look out for, any events or projects which would be beneficial?
I don't know, I would probably, if you're interested, like when I was a kid, I used to buy electronics stuff. There was an electronics shop where I lived. So I think if you are interested, buy get yourself a kit for Christmas. There's so many kits available now in terms of, well, you want to study aerospace, but if you're interested in robotics and these sort of applications, there's so many kits that are available. There's so much information available on the internet now to help you learn that I think that would be beneficial for eventually you'll write a cover letter. So I feel like that would be benefit for your cover letter to say that you enjoy doing X, Y, and Z in your free time.
Yeah, I think that's kind of the advice I got. We're trying to remember back to quite a few years ago. But yeah, I think it's just about showing some kind of interest in your topic. And it is quite hard outside of but even, I mean, I think the most boring one is to read a book about a subject and talk about that. But I think doing a project or doing some online courses or that kind of thing is a bit more of it. Bit more proactive, and if you have interviews, then it's something a bit more interesting to talk about as well. So I think what you're suggesting,
I think learn by doing is really, really good, and it's something that I'm kind of very keen on. But do not get too distant away from the theory, because the theory normally explains what you're expecting to see.
So if it's like aerospace, and you could do a coding project or something. Try and design an aerofoil. That's good. My challenge. Depending on what part you're interested in. Another question about when you're tuning the PID controller. So were you able to simulate instability? Does it do that in the code?
So I assume you're talking about, because you're talking about simulation, so you're talking about the model design approach. So depending on I did actually, when I was tuning this, it did actually go unstable a few times. But what you'll notice here is, if some of you that are kind of aware of this, you'll see that I've got discrete time for my PID, and I've actually got continuous time for my system, because the package that I use enables me to effectively mix up modeling domains, which you can't do if you're doing hand calculations, but you can do it in this package. So it would convert it all to discrete time. So certain discrete, so proportional control gain values, the system does become unstable, because I don't know if you can relate back to your theory, when you're looking at discrete time, you have something known as the unit circle, and what happens is you increase the proportional control gains is effectively move outside the unit circle, where outside the unit circle it becomes unstable. So I did get that when I was tuning it. I increased the proportional gain too much, and then the system response just goes unstable.
Okay.
This particular application in practice, though, it's I think instability, the increase of proportional. I did actually play around a little bit with an integral, but it did go a little bit funny. So I think it's the type of system, maybe an integral is not needed.
Yeah. Okay. I can't answer this question, but if you move the Rubik's Cube backwards, i.e. nearer to the model car and closer than the target distance, does the car move backwards?
Okay, that's a good question. At the moment, what you'll see on the screen at the moment, I've got something known as, although I didn't go over the electronics because I didn't want to get bogged down in detail. What you notice is I've got a H bridge, or a motor driver. So what I can do, although it's not wide up to do, I could have got it to reverse. So I can get it to go up. And say if it was to overshoot, and I could get it to basically do something like that. Because the H bridge, what it enables me to do is to effectively reverse the polarity of the motor. And by that, I mean, effectively, if you've ever got a red and a black wire and put them on a DC motor, it's going to spin, swap them round, it's then going to spin the other way around. That's what that H bridge does. It just basically changes the spin of the motor. And I could have configured that within the algorithm on board here to effectively, to get me to do something like that. But the current car that I've got there, no, it doesn't, because I just configured it basically just to go forward and to slow and hopefully stop at 0.1 meters away from the object. Yeah.
Okay. Somebody's put in, not really a question, but they've just said it's been a good lecture, and providing the contacts and things like that. So, and there's lots of thank yous as well that had came up in the chat as well. So, and then someone, I'm not sure if someone's asking about stability tests. Nyquist, I don't know if that relates to something that you've said already,
Nyquist, that's this one. There's lots of different stability tests, and thank you.
Thanks a lot, everyone.
Cheers, thank you everyone for attending.